Okay, guys, hopefully by now you have had ample time to review your concentration module that is co-written by Dr. Sandra Barnes um, and her colleague, um, Dr. Dave Thompson from Sam Houston State University. I hope that you have read through it thoroughly and have considered the questions that have been posed. And the purpose of this little video today is to kind of focus some of the things, the takeaways from that module that I want you to make sure that you take forward into the next part of the semester, as well as to formalize the questions that I want you to answer for your midterm assignment. Okay? So, like I said, the module that you have been assigned was developed by Dr. Dave Thompson from Sam Houston State, Dr. Sandra Barnes from Alcorn State. The importance of this module is that it will give you a foundation to understand the methods of calculating concentration and expressing concentration or relative abundance as you move forward in your chemistry careers, whether you go to medical school, whether you go to dental school, whether you go teach chemistry, whether you are a field chemist or a researcher, whatever. It is very important to understand the true relevance of expressing amounts in terms of concentration. So the first thing we're going to consider in wrapping up the main points in this module is what is relative abundance, its units, and why is it so important that we understand the meaning of relative abundance. Throughout your studies, you have been exposed to relative abundance in terms of concentration, mole fraction, all different types of ways to express the substance that we're interested in measuring versus the amount of the entire sample. But this module actually gives you some pretty unique ways to break down each one of those types of measurements to make it more clear for you going forward, to help you to understand the appropriate times that you will need to express a concentration in a certain unit versus another unit for a different scenario. Your module actually gave you some examples, and it asked you to reflect on the importance of several different cases. It asked you to reflect on the importance of knowing the concentration or relative abundance of a particular substance in various scenarios. So, for instance, it gave an example of a police officer who is testing a suspect for a suspected DUI. It would be important to know how much abundance of alcohol would be present in the suspect's blood relative to the total concentration of blood, right? So the blood alcohol concentration. On the other hand, it gave some other examples. A farmer who is spraying his crops with a pesticide. Why would it be important for the farmer to know exactly how much pesticide? What would be the impact if the farmer put too much pesticide on the crops, in terms of the crops and in terms of the end user, the consumer who may ingest too much pesticide? So you could look at it in terms of, if he puts too little pesticide, then the weeds may take over or the bugs may take over. If he puts too much pesticide, the crops could suffer. The pesticide could be taken up by the plant and then end up in the bloodstream or in the body of the folks who eat it. So it's very, very important to have accurate measurements of concentration, accurate ways that we can both measure concentration and express concentration to the person who needs to have that information. Now, depending upon who the ultimate end user is, who is the person that needs the information, we will express the concentration in different ways. Okay, so that was a quick introduction to what we're going to talk about to wrap this chapter up. One of your assignments that was given to you in the module is to consider the series of people who I just talked about: the anesthetist who will be in the hospital, the diabetic who needs to know his or her blood sugar level, and consider the importance of these different folks in knowing what the concentration of a particular substance would be and the potential impact in their lives for miscalculation or et cetera, et cetera. Okay, so that is one of the activities that I would like for you to actually turn in from the module. And I will probably take it out of the module and give you the questions separately. But I hope that you have considered those questions and are ready to just answer them. So the module that you have read and have gone through, it is apparent as you have read that everything that we will be discussing in the module in terms of theory, we're going to do it in the context of a molecule called quercetin. Quercetin is a very unique compound in that it is found in various places. It's both found in fruits and vegetables as an antioxidant or free radical scavenger that is very beneficial to the body. It helps to protect our cells from damage and other biomolecules in our body from damage. Another area that quercetin is very beneficial is as a dye, and especially for the cosmetics industry, it can act as a natural dye or colorant, and it also can be used in the textiles industry to color our clothing and other items, and it can be used in terms of nutritional supplements. So quercetin is a very versatile compound. It has a high degree of importance. You will see, I don't know if you've noticed, but in recent years, I know you've heard a lot about antioxidants and free radical scavengers and things like that in terms of nutritional drinks. But a lot of times, the health food companies, the sports drink companies will excuse me, will, what's the word I'm looking for here? I guess will play up the quercetin content in their drinks because it is a very, very powerful compound. Okay, so the fact that this compound has so much versatility, the other component of the module, part one of the module, was it asks you to go and look at PubMed, which is, it gave you the website, it gave you the web address, and it gave you specific instructions to go and look up different articles to determine what some of the uses of quercetin are, and to look and see how the individual articles reference quercetin in terms of concentration. Do they reference it in milligrams per liter? Do they reference it in milligrams or grams per liter? Do they reference it in terms of mass percent? So basically, that activity too, I also want you to do, but you don't have to go as in depth as they ask you to in the module. I just want you to go look at PubMed, find 5 different abstracts. I want you to go to PubMed Central, actually, find 5 different abstracts and read through the abstract and describe the use or the way that quercetin is used in the paper. What types of studies were done on quercetin? What is it about quercetin that you actually were able to learn from the paper? And also, what types of ways do the authors express relative abundance or concentration? Okay, so that's activity 2. So I'm going to take that out separately and put that in your midterm questions as well, for you to just go and do that activity. And I'm going to want you to do this as part of a discussion board after midterm. So for right now, that's going to be activity 2. I'm going to put the specific questions that I want you to answer regarding that in a separate Word document. I'm going to take it out of the module so you'll know exactly which ones of these questions that I expect for you to answer. Okay, so basically, up to this point, we understand the importance of relative abundance and concentration. We know that we're going to be learning or reiterating what we know about relative abundance and concentration, and all of our activities are going to have something to do with a question related to quercetin. And in doing so, you not only will learn about relative abundance and concentration, but you also are going to get a greater appreciation of the role of quercetin in our society and learn more about quercetin as a compound. Okay? So look at your second set of questions that I'm going to post in your assignment document that will relate to what I want you to do for quercetin. So now let's move on into actually describing relative abundance. And before we do that, the module gave you a scenario where it asks you to consider an apple. An apple, which is a lot of wholesome, nutritious components, and they're all present in the apple. You've got proteins, you've got a little bit of fructose sugar, you've got water, you've got quercetin, which we just talked about. You've got all kinds of vitamins and minerals that are all a part of the apple. Okay, so let's say that we took a piece of the apple. Okay, let's say we took a little piece of the apple off and we want to measure how much quercetin or how much of another component is in that portion. Okay, so the portion that we took off to measure is called the sample. And the specific entity that we're interested in knowing the concentration of is called the analyte. So if we are trying to determine how much quercetin is in this little part of the apple, then quercetin is the analyte, and this part of the apple is our sample. So depending upon who it is that we're doing this measurement for, and depending upon a lot of other factors, then we can determine what our relative abundance units should be in expressing how much analyte is present in the sample. Okay, so the relative abundance, which is the subject of this entire module, describes how much analyte is present in a specific quantity of sample, which is what I just said. So if we have this little chunk, the first thing we need to understand is how much of that chunk, what is the amount of sample? The amount of sample is just as important as the amount that we are trying to measure of the analyte. Okay, so amount of analyte in a certain amount of sample. So how much analyte do I have relative to the whole sample? That's why it's called relative abundance. How much analyte is present relative to the other components in the sample. Okay, so for example, we will measure the amount of analyte in either mass, moles, or volume relative to the sample in mass, moles, or volume. Okay, so let's keep it moving here. And I think we got the point. If we're talking about a specific analyte relative to the whole apple, then the apple would be the sample, and the total mass or the total moles or the total volume of the compound that we're interested in would be the analyte, the total concentration, the total amount. All right. Now, knowing that your sample is going to be measured by either a mass, moles, or volume, and so is your analyte. So your analyte is going to be measured in mass, moles, or volume, and so is your sample, mass. And so when we're talking about the mass of the sample, we're generally talking about the total, the whole, the mass of the total sample, the moles of the total sample, or the volume of the total sample. Okay, so basically, mass of A, moles of A, or volume of A, and mass of total, moles of total, or volume of total. So if we know that in order to express relative abundance, we have to have a numerator that talks about the analyte and a denominator that talks about the whole sample, then we can have any of these in the numerator and any of these in the denominator. And when we do so, we are conforming to the definitions that are given by the International Union of Pure and Applied Chemistry that describe relative abundance in three categories. The first one is concentrations, which have a volume unit in the denominator. And the second one is units that have, measurements that have the same unit in the numerator and the denominator. And the third one is molality, which is a separate category all of its own. So if you will recall, you have heard me use the word concentration a lot because as chemists, that's what we're really accustomed to talking about is concentration. We talk about molarity all the time. Molarity, concentration. But the International Union of Pure and Applied Chemistry, IUPAC, has three separate categories to describe relative abundance, and concentration is only one of them. Concentrations, we're going to talk about each one of these individually, specifically in the next slide. But basically, the defining characteristic of concentrations is that a concentration has a volume in the denominator. For fractions, the defining unit is that, the defining characteristic is that the same base unit is in the numerator and the denominator. And for molality, the defining characteristic is that we're talking about the unit in the denominator as being the solvent and not the entire sample, just the substance that is present in the largest amount. So the one thing that is common for all of these is that we have a numerator that talks about the amount of analyte, and a denominator that talks about the amount of sample. And in doing so, that gives us a ratio, and that's where the relative abundance comes from. And I know I keep stressing that, but I want you to make sure that you commit that to your thought process, and that's what you always are thinking about. Relative to the entire sample, how much analyte do we have present? And that when you divide a numerator by a denominator, you will end up having that as an expression of relative abundance, okay? All right, so let's take the first one. Let's take them one by one. The first one was concentration, okay? So we have these three categories, and the first one we're going to look at is concentration. All right, so concentration, if we have a whole sample of something, okay? So if this is a glass of something and it's filled all the way to the top, our concentration of this analyte is going to be relative to the entire volume after mixing the sample together. Okay? So, knowing what we said a few minutes ago, the distinguishing characteristic of a concentration is that volume is in the denominator. And specifically, the volume of the solution in this case after mixing. Okay? So the volume of the solution is in the denominator. I can't talk all of a sudden. Let me see if I can erase this line. I obviously cannot. Okay, at any rate, then we know that the solution volume must be in the denominator. And what do we know about the solution volume that we saw in the one of the previous slides? Is that the solution volume represents the total volume of the solution. So V total, volume total of all entities of quercetin, if we're talking about the apple, of the fructose, of the water, of the calcium, of the ascorbic acid, the vitamin D, everything that's in that apple, whatever the total volume of everything is, then that's what goes in the denominator. Okay, so what goes in the numerator is dependent upon how we measure the analyte concentration. If we measure it in amount, which is the SI unit for chemical amount is in moles, the SI unit for mass is grams, and the SI unit for volume is in liters. So knowing that, remembering that the analyte over total is what we looked at. And so if we know that in each one of these cases that the total volume is what's going to be in the denominator, then let's look at what we would end up with in each one of these cases. So in terms of amount, the amount in number of moles of the analyte over the total volume of solution, okay, and generally that will be in moles of analyte over liters of total solution. So what does that look like? From all of your courses previously, your quant, your general chem, and coming up in chapter 7 in your pchem. So that looks like molarity, right? That looks like concentration in moles per liter is the same thing as molarity. So you're accustomed to seeing that already, but this just follows our little pattern that we've been looking at. So now let's look at the second scenario. What if we were to take now mass in the numerator? So you have mass of A over volume total, and then your SI unit of mass we said is grams, in your volume. So you have grams of A, which is your analyte, in your liters of total solution. So you end up with grams per liter. So you should recognize this mass over volume. We call it a concentration here, but that looks a lot to me like the density equation. So basically the density of a solution can be referred to as a concentration if we take our definition of having the solution volume in the denominator. The very last one, if we have the volume in the numerator, which is volume of A, and the volume in the denominator of the total solution, then we end up with SI unit of A in liters versus the SI unit of the total in liters. And so as you can see, liters in the numerator over liters in the denominator would give you a situation to where your values here should cancel out. And so this is identical to the second definition of relative abundance that we're going to talk about on the next slide, which is fractions. So even though this is a concentration because it has the liters of total solution in the denominator, then you're going to see that this is the same as the volume fraction that we're going to see in the next slide, okay? So I had recorded the slide previously and did not like what I told you. So I was going to come back in here and tell you something completely different and erase all of this stuff out. So I'm not going to, but I obviously can't erase what I had previously written. So first of all, I'm going to just give you the definition here, and then we're going to move to a blank slide in order for me to write what I'm trying to write, okay? So this slide is going to deal with fractions, okay? So fractions define relative abundance as a ratio of the analyte, the ratio of the total quantity of all components in the sample before mixing, okay? So we're talking about the ratio of everything in the sample, blue and red. So basically the ratio of red to the ratio of red plus blue, right? So the ratio of the analyte that we're trying to measure over the total sample, which includes all components, component 1 plus component 2 plus component 3 plus component 4 plus component 5. And we're talking about this analyte in terms of the total components relative to mass, moles, or volume. But for a fraction, the distinguishing characteristic is that the same base unit must be in the numerator and the denominator so that those units will cancel in order for you to get a fraction. So I'm going to open up or go to a fresh blank slide in order to do that. And it is not letting me go to a new page. Okay, yes it did. All right. So since we know that each one of these then is the same difference, if we're talking about a mass fraction, then we must be talking about mass of analyte over the mass of the total sample. That means the grams or mass of component 1 plus component 2 plus component 3 plus component 4. The SI unit of mass is grams, so the grams of analyte over the grams of the total sample. And then, of course, your grams will cancel in terms of a fraction. And you'll be left with a fraction that is called a mass fraction or weight by weight fraction. Why is that? Because you're talking about weight of analyte divided by weight of total, so weight over weight. Okay? All right, now if we're talking about moles, you're talking about moles of component A, which is the analyte, the thing you're trying to measure, over the moles of the total of everything in the solution, everything in the sample, the moles of component 1 plus the moles of component 2 plus the moles of component 3, etc., okay? And so the SI unit, of course, for moles is, for amount, is moles. And we express that with N. So we're talking about the moles of A over moles of total. And of course, your moles would then cancel. And then you would get a moles over moles fraction. So you know what that's called, right? I just said it. That's called a mole fraction. So we usually define that with the symbol chi, mole fraction of a mole fraction of your analyte. You've seen that before. Number of moles of analyte over total number of moles. On the other hand, the other way that we measure things is volume, that we've already seen in the previous slide. Volume of analyte A over total volume of sample T. If we're talking about SI units, the liters are the measurement in SI units for volume. Liters, analyte. So just like in our concentration slide, we're talking about volume of component 1 plus component 2 plus component 3. We're talking about the total volume of solution. The only thing that's different here, it looks exactly like the concentration slide where you have liters of analyte over liters of solution. And it actually should be about the same. However, in PChem, we're going to learn that the individual volumes of each component are not necessarily additive. So the liters total before mixing of individual components let me see, how do I write this? Okay, so the liters total of components may not be equal to the total volume of solution, because when you mix, may not be equal to, okay, because when you mix components together, the intermolecular attractions cause, or repulsions may cause, a different arrangement in the solution that cause the molecules to spread out or contract. So your total solution volume may be slightly different than the volume of each one of your individual components mixed together. Okay, so although the relationship looks the same, where you have the volume of the analyte in the numerator and the volume of the total solution in the denominator, the fractions are exactly the same in this case and also the case we saw previously. But because of that factor, then your volumes may not necessarily, this might not be exactly the same value. But for all practical intents and purposes for this particular course, we're going to say that it's pretty similar. Okay? All right, so moving on. So the last thing that we have to consider in terms of the IUPAC categories that describe relative abundance is molality. Molality defines relative abundance as the ratio of the moles of analyte to kilograms, not of sample, but of solvent. And of course we know that the solvent is the compound or the part of the sample that is present in the largest quantity. Okay, so basically, in this case, we're talking about the moles of the red thing and the kilograms of the rest of it, the solvent, the purple thing. So moles of A and kilograms, not total, but kilograms of component B, which is the solvent. Now, we may have component A, B, C, D. Let's just call this component, let's just call it solvent because I don't want to confuse you. Because if you have a whole bunch of different constituents in the sample mixture, then the kilograms is going to not refer to anything but the component that's present in the largest quantity, the kilograms of solvent. So this is the defining characteristic of molality. We are not talking about the total solution. Remember, in concentration, we were talking about the total solution. We said that, okay, we're talking about the whole thing, including the analyte. No, we're not talking about that. We're talking about just the solvent. Just the solvent. So, and not just any quantity of the solvent. We're talking about specifically the quantity of the solvent in terms of its mass in kilograms. Okay? And we define solvent once again as the component in the sample that's present in the largest quantity. So that is equal to molality. N over mass in kilograms of solvent. All right. So now, when you use each one of these expressions of relative abundance, is going to depend on several different factors. Well, first of all, let's get our concentration, we got our fractions, and we have our molality. Now, like I was saying, how do we know which units to use? You have two defining criteria. All right. The first one is, who is our audience? What is going to be the best way to describe this amount or this relative abundance to our audience? And the second is, which ones are most straightforward, measured in the most straightforward fashion? So, for instance, solids are much more easily measured by mass. Gases and liquids, on the other hand, are much more easily measured by volume. If we're talking to someone who's not a scientist, then we are pretty much probably not going to express amount in terms of moles because that really has no meaning for them. So depending upon who we're talking to and how easy it is for us to measure something, then we determine what units that we will use. Okay, so here's an example. Once again, we see our compound quercetin, the one that we say we're going to keep talking about a lot in this unit. And here's an example of a scenario where quercetin measurement will be important. A chemist measures the relative abundance of quercetin in an apple for an apple farmer. Okay, so the apple farmer wants to know what the relative abundance of quercetin is. How should the chemist report back their measurement to the farmer? So why would an apple farmer want to know this? So basically, if an apple farmer has a good crop, then he would like to be able to market this as a crop of apples probably that is high in antioxidant content, high in quercetin content. So he would probably want to be able to tell the farmer's market or the consumer or the wholesaler or whoever he's selling his fruits to the amount of quercetin present. But for him to be able to understand that, and for him to be able to report that, and for him to be able to express that to the end user, the consumers, the folks who are going to be eating this, then what units do we need to report this to him in? When we do that, we first consider criteria 1 and 2 for both the numerator and the denominator. First, the numerator. What goes on top? So criteria 1 is who is the audience. Criteria 2 is what's most easily measured. And we go from there. All right. So criteria 1. All right. What goes in the numerator? Criteria 1 is that it's a farmer. So do we want to express the numerator to a farmer in terms of grams, moles, or liters? So, all right, we could express it in terms of something that he or she could understand. Moles would be probably not useful. Grams or liters would be the best bet. But it's a solid compound, it's an apple. So we probably wouldn't want to use liters because that's more difficult to measure than putting an apple on a scale and saying, okay, for every 5 gram or 20-gram apple, then you've got X amount of quercetin. Okay, so that's the numerator. So it's probably best for us to express grams as the unit in the numerator. So what about the denominator? All right. Once again, for the audience, moles is probably out. Okay. So we're left with grams or liters. And once again, for the same reasons, liters is a volume. So we probably wouldn't want to liquefy our solid apples to volume in order to tell somebody what the concentration is in, in liters if we're a farmer. So it would be much, much better for us to say grams of analyte, which is what goes in the numerator, over grams of total sample, or mass analyte over mass total. So basically a fraction would be most useful for this scenario for the farmer. So you have a few of these different scenarios that constitute exercise 3 of your assignment, where there, I think, are 5 different scenarios where it asks you 5 different types of industry, 5 different types of end user, where you are going to be asked, or where you have been asked. And I hope that you've had an opportunity to read over that, where you are asked what the employee, employer, what the person in the context of the question, what type of measurement we should use in order to report a given quantity of quercetin in a given sample to a specific audience. Okay, one is like a cosmetic engineer, I think. One is, you've got different scenarios. So go through those, and that's going to be one of the question sets that you'll need to answer for your midterm activity. Okay? All right. So one of the things that your module gives you in helping to make those decisions is to consider a raw sample versus an instrument-friendly sample. So a raw sample is something that has not had any processing. Okay, it's not something that we've been able to bring back to the lab and liquefy and get it to where we purify it and prepare it and prep it and get it to where we can put it in the instrument. So this raw sample is usually the types of sample that we would consider for people who are not scientists. Okay, so that was one of the considerations that your module reminds you to take, to undertake. Once again, I can't talk. That is one of the considerations that your module reminds you to consider. Is it a raw sample or a sample that's an instrument-friendly sample? And so I've kind of given you the distinction between the two. And I already told you about the fact that solids are generally more easily measured by mass. Liquids are more easily measured by volume. Let's see. Okay. All right. Yeah, and other consideration that we had was what is most useful for the end user, the farmer in this case. Now, this just kind of goes with the little example that I just gave you that we've already solved. So this is just further explanation of the example that we looked at a few minutes ago, but it also gives you a little bit more of information of what you can use in order to answer the questions that I told you that you're going to have. Okay? All right, so knowing that that was a raw sample and that's most commonly used in the field, and that's what end users, farmers, consumers, folks who don't really need to do instrumental analysis or processing of the samples would encounter. What is an instrument-friendly sample? So a lot of times we can place these raw samples, such as a piece of an apple, or you can go out to the stream and take the sample directly from the field and do an analysis of the amount of iron, for instance, or lead or arsenic, for instance, directly from the sample. But more often, it's not very convenient or practical for a chemist to be able to do that because the sample will require processing. So a lot of times we want to turn our samples into liquid solutions in order that we can process them, in order that we can analyze them more easily. So this liquid solution would be in the form of a homogeneous mixture that is transparent and uniform in color, uniform throughout. Just like any other solution, the most abundant liquid is what we call the solvent, and the distinct compounds that are dissolved in the solvent are the solutes. Okay. Now, sometimes the analyte is actually the solvent. Sometimes the analyte is one or more of the solutes. But knowing what the components of a liquid solution are, solvent is the thing that's present in the highest abundance. Solute is the thing that's present, or are the things that are present in the smaller quantities. But knowing that just allows us to be able to identify what we want to measure. Okay, so we can, by definition, our analyte is just the thing that we want to study. So we can study the concentration of the solvent, or we can study the concentration of the things that are dissolved, the solute. So it doesn't really matter which one. The sample is what we're testing. The analyte is what we want to know the information about. That can be solute or solvent. Okay? So this is just basically solute, solvent, definition of a solution. Definition for analytical purposes is that the sample is the substance that we are sampling, and the analyte is the thing that we want to know the concentration of. Okay? So most of the time, when we're talking about solutions that are instrument friendly, that a chemist would use in their measurements, most of the time we're talking about liquid samples that have a volume of the solution in the denominator. So most of the times we're talking about the mass in grams of the analyte over the volume of the solution in liters. Volume total after mixing, right? because that is concentration. So we usually measure instrument-friendly samples, the things that we care about as chemists, in concentration. So this is most commonly, if it's milligrams or some base unit version of grams. Or, on the other hand, we can call it moles of our analyte over volume of the total solution. And of course, that would be in moles per liter, or molarity, like we are accustomed to reporting it in. Okay, so for folks in the field, we usually don't like to talk about moles and concentration like this for most part. I am getting sleepy, so I'm starting to talk in circles here, but I hope you get the point. Okay, so if this is confusing in any way, refer to the module, look at your units that they use in order to describe these different scenarios, and then give me a call or email or come by my office during office hours if you have any particular clarifications that I need to make for you. Okay, so like I say, for the exercises that you're going to have for this particular part of the module, I'm going to put those, this is going to be part of it, but you can ignore this from this slide because I'm going to specifically type them up and put them in and assign them to you in a concise format so you can see exactly which parts that I want you to concentrate on, okay? So that's going to be part A of your midterm assignment. Part B of your midterm assignment is going to come from the conversion, how we convert these relative abundances from one type of unit or one type of relative abundance to another. And this is something that I know you've read thoroughly in your module. I'm trusting that you have. And I'm also trusting that this was a review for you and more in-depth enrichment for what you've already seen. And so this is part A, that's going to be part B, and that's going to constitute your total midterm assignment. And I probably will go ahead and do, I guess I'll do a video review for that too, just to make sure that we're all on the same page as to how we convert between those. But I'm going to give you your typed up assignment that specifically spells out exactly what I want you to do, so that there's some parts in the module that I'm going to allow you to skip. So I'll pull from there the specific questions that I want you to answer. Okay? And so after you do that, I want you to save your questions because I want us to come back after the midterm and discuss some of these things on Blackboard in terms of in the form of a discussion board. And then we're going to move right into our experiments. Okay, so have fun with this. I hope that this is truly helpful for you, especially as you move forward into your other classes where concentration is going to be something that you're supposed to know off the top of your head. Now, the other thing that is in your module that I encourage you to do is they have a section that they ask you to go through a series of steps to help you memorize these concentration units. I strongly suggest that if you have not done that, that you do that. Because it's not only going to be helpful for you in this class, you'll probably, since it's an online class, you will always have those things in front of you, but it is going to be so critical for you to be able to quickly recall those things, especially when you get on your standardized exams and where you don't want to always have to look back and say, okay, what is mole fraction again? What is mole fraction? Okay, what is molarity? Okay, what is weight by weight? Okay, what is this? You don't want to have to do that, okay? So go ahead and do that exercise in your module that shows you how, or that takes you through some ways that you can memorize these more easily. Alrighty, and so I will see you in the next video in part B of your midterm assignment. All right.